All right, you guys, so we're gonna do a little bit of distance learning here. I've lectured on 3.1 and 3.2, and in the Google Classroom you guys should have assignments for those. I'm gonna lecture on 3.3 today. I'm gonna upload the PowerPoint that goes with it, and the worked out solutions, so that you guys have a way to interact with that. So here we go. So this section we're going to talk about direct variation and inverse variation. We're going to start with direct variation. So y varies directly with x, or y is directly proportional to x, if there's a non-zero constant such that y equals k times x. That's important because with inverse variation it's different. K is called that constant of variation or the proportionality constant. Make sure you guys have that formula down somewhere. So example one, we're supposed to write the variation equation for these statements. So you got to figure out what variables you know or you're talking about, and the k is always going to be that constant. So for number one part A here, wages earned, let's call that W, vary directly with the number of hours worked. Let's call hours H. So wages earned varies directly with the number of hours worked. Okay? That's all they're asking you to do in these problems. So let's look at B. The value of an office machine varies directly with time. Okay, so let's call the value of the office machine V, and it's varying directly with time, so we'll let that be T. So the value of the office machine, V, varies directly with time. Like so. Why don't you guys take a second, pause the video, and try C on your own. Okay, let's see how you did. The circumference of a circle, let's call that C, is directly proportional to the length of its diameter, so D for diameter. So circumference of a circle is directly proportional to the length of its diameter. How'd you guys do? All right, let's move on. So if I have an application problem where they give me a couple of numbers that vary directly, and I want to find that constant of proportionality and then use it to predict something in the future, I'm going to follow these steps. So I'm going to translate the information given into an equation model using k as the constant of variation. That's what we did on the previous slide. We're going to write a model. Two, we're going to substitute the first relationship or pair of values given. So they're going to give you a couple of different numbers that we can put in place of those variables. And then we're going to solve for k. We're going to substitute the value for k into the original model to obtain an equation that works for all models. And then we're going to use that equation to predict. Okay, so let's take a look at an example. The weight of an astronaut on the surface of another planet varies directly with the weight on Earth. An astronaut weighing 140 pounds on Earth weighs only 53.2 pounds on Mars. And we're supposed to find out how much a 170-pound astronaut would weigh on Mars. So step one, we're supposed to figure out that direct variation equation and then eventually solve for k. So the weight of an astronaut on another planet, we'll say Mars, varies directly with their weight on Earth. So let's call that E. So that's our general formula for this. Now they've given us some information. They've told us that someone that weighs 140 pounds on Earth, so I can replace E with 140, weighs 53.2 pounds on Mars, which would be what I would replace M with. That'll allow me to solve for K. So 53.2 pounds on Mars to 140 pounds on Earth. Just substituting those values that I know. Okay, so I've got a little bit of work to do on the calculator here. To solve for k, I'm going to have to take that 53.2 and divide it by 140. And I get 0.38. So now I know my constant of variation, and I can write a general equation that will cover all of those scenarios. So my general equation here is going to be that somebody that on Mars is going to be 0.38 times what they weigh on Earth. So that will work in general. Step 4 then is to go through and actually use that new equation to predict what we've got here. So how much would a 170-pound astronaut weigh on Mars? Well, that's their Earth weight, so I can put that in for E. And then grab my calculator, 0.38 times 170, I get 64.6. So a 170-pound astronaut on Earth is going to weigh 64.6 pounds on Mars. That's how you would apply those 4 steps that we were given on the previous slide. Okay, let's look at another one. The scientists at NASA are planning to send additional probes to the red planet Mars that will weigh 250 to 450 pounds. Graph the variation equation from example 2, then use the graph to estimate the corresponding range of weights on Mars. So again, from example 2, if you recall, that was our equation. Well, grab your calculator, go into your y equals, and put 0.38 e, or 0.38x. I have 53.2 divided by 140, the same thing. So this is what I put in my y equals, you guys, that 0.38 times x. Now, what we can do is, because we're in the graph for this, we can use the trace to help us predict, although we got to be a little bit careful. We got to make sure our window is set up to handle this. So x in this case represents the weight of somebody on Earth. So we need to put in some potential numbers. They want us to predict what's going to happen for people that weigh between, or equipment that weighs between 250 and 450 pounds. So I need my window to go out to maybe 500. So I'd have your x min be 0 and your x max be 500. Okay? And then in terms of the weight on Mars, we knew a little bit about a 170-pound person. That was 64 pounds or so. We know that 450 is going to be higher than that. So we're guessing a little. I set my window to 200. So I went 0 for the x, or the y min, excuse me, and I went 200 for the y max. And then I graphed it. Okay, you get this nice line. If you press trace, you can simply type in 250 then, and it's going to spit out the corresponding weight on Mars. So a 250-pound piece of equipment is going to weigh 95 pounds on Mars. A 450-pound piece of equipment is going to weigh 171 pounds on Mars. Of course, we can get those same 2 numbers by just plugging those values into that equation. If I take 250 times 0.38, I'm going to get 95. If I take 450 times 0.38, I'm going to get 171. That's going to be the range of weights on Mars. Okay? Just a different way to look at it, looking at it graphically versus an equation. Okay, example 4, write a variation equation for these statements. So now it's not going to be necessarily linear, but it's going to be similar. Okay, so it says in free fall, the distance traveled by an object, let's call that d, is directly proportional, so a k involved, to the square of time. So let's call time t. So the distance is directly proportional to the square of time. So I'm supposed to square that second variable, so kt squared, all right? Similarly, b, the area of a circle, oops, pardon me, area, the area of a circle varies directly with the square of its radius. So let's call the radius r, and we're going to square that. This is what they're asking you to do, is come up with a model for this. Eventually, if we were given the radius and the area, we could predict what k was going to be in each situation. Okay? So how about this one? The range of a projectile varies directly with the square of its initial velocity. As part of a circus act, Bailey, the human bullet, is shot out of a cannon with an initial velocity of 80 feet per second into a net 200 feet away. Okay, find the constant of variation and write the variation equation. Okay, fair enough. So the range of a projectile varies directly with the square of its initial velocity. So that's what our model looks like. The second thing they asked me to do is find that constant of variation. Well, I do know some things. Okay, I know that the initial velocity is 80, and I know that the range is 200. So I'm going to put in what I do know and I'm going to solve for k. So I know the range to be 200 k times 80 squared. So I'm going to grab my calculator and I'm going to take 200 divided by 80 squared to approximate k. That gives me 0.03125 for k. So my variation equation then is going to be R equals k, which is that 0.03125, times velocity squared. Okay? Keep that equation, write that equation down somewhere, keep it in the back of your mind because we're going to use it here in just a little bit. But that's how I'm going to generate it. Very similar to those 4 steps that we did a couple slides ago. Okay? Graph the equation and use the graph to estimate how far away the net should be placed if an initial velocity is increased to 95 feet per second. Okay, so in my y equals 200 divided by 80 squared, that's that 0.03125, times x squared. X in this case represents my velocity. Okay, so I can put that into my y equals. Got to be a little careful about window, you guys. So x represents velocity. We know we're going to go all the way up to 95 feet per second, so I went from 0 to say like 150 for x. And the range, I'm not sure. I know that for that initial velocity of 80, the range was 200, so I know I'm going to have to go higher. So maybe if I go from 0 to 300 for my y min and my y max, I think I've got a window that will work. So I graph it. I go to trace again like we did on the previous graph. I type in 95, and it spits out 282.03125. So if a person is shot out of that cannon at 95 feet per second, they can expect to fly a range of 282 feet. Okay? The same as taking 0.03125 times 95 squared, we're going to get the same result. Okay? So now, determine the accuracy of the estimate from B using the variation equation. Because we use the actual model and we put 95 into the equation and then use the calculator to predict it, it's very accurate. Had we just eyeballed it from the graph, we would have been less accurate, but that's very accurate because we use the actual model. Okay, we're going to switch gears a little bit. We were talking about direct variation, which was y equals kx, to inverse variation. So y varies inversely with x, or y is inversely proportional to x if there's a non-zero constant such that y equals k divided by x this time. Not times x, but divided by x. That's called the constant of variation, or the proportionality constant that k is. Okay, so it's k over x this time. So write the variation equation for these statements. The time it takes to complete a road trip, call that t, varies inversely, or is inversely proportional, so k over the average speed, s. Okay? The intensity of light, let's call that L. We got to have some variable for it, but be as descriptive as we can. Varies inversely, so it's going to be k over the square of the distance from the source. Okay? Like so. Those problems are simply that. They're asking you to write a model that would match that. Eventually, we're going to go through the process to solve for k and predict like we did with direct variation. But for now, we're going to stick with just writing the equation. So Boyle's law tells us that in a closed container with a constant temperature, that's important, the volume of gas varies inversely with the pressure. So volume varies inversely with pressure. Suppose the air pressure in a closed cylinder is 50 pounds per square inch when the volume of the cylinder is 60 cubic inches. Find the constant of variation and write the equation. Okay, so tells us that in a closed container, volume varies inversely with pressure. So volume varies inversely with pressure. That's going to be our general model that we're going to work from. To find the constant of variation, we can substitute what we know about one of the examples. We know that the pressure was 50 pounds and the volume was 60 cubic inches. So I can say, I'm going to work down here for a little bit, you guys, that the volume of 60 cubic inches is K over 50. Well, to solve for K, I'd have to multiply both sides by 50, and I'm going to find that K is equal to 3,000. Okay? So the constant of variation, got it, 3,000. Write a variation equation. So volume is equal to that constant of variation over pressure. So that's going to be that variation equation. And now I've got a model that can help me through just about all of these. So for B, use the equation to find the volume if the pressure increased to 150. So now I can replace that P with 150. So if I take 3,000 divided by 150, I get 20. Okay, so 20 cubic inches. So as the pressure went up, the volume went down, and that's what it means to vary inversely. Okay? All right, the amount of fuel used by a certain ship traveling at a uniform speed varies jointly. So we haven't talked about joint variation. It's a lot like direct variation, but we've got more variables. That's all it really boils down to. So we're not dividing it all here, we're multiplying just by several variables. So the amount of fuel used by a certain ship traveling at a uniform speed, so amount of fuel, let's call it F, varies jointly. There's still going to be a constant of variation there, you guys. With the distance it travels, call that D, and the square of the velocity. Okay? That's what joint variation is going to look like. If 200 barrels of fuel are used to travel 10 miles at 20 knots, how far does the ship travel in 500 barrels of fuel at 30 knots? Okay, so what we need to start with is we got to find K, you guys. And so I'm going to go ahead and plug in some of the knowns, solve for K, and then use our model to solve the second part of this equation. So if 200 barrels of fuel are used, well, that's going to be that fuel capacity. That's your 200 here. To travel 10 miles, that's a distance. At 20 knots, nautical miles per hour, that's a velocity. Okay? I have everything I need except for K, so I'm going to solve for this now. So think to yourself what you would do to solve this. I'm going to have to take 200, and I'm going to divide it by the 10 and the 20 squared. Okay? And I'm going to get, oops, I typed in the wrong thing here. I'm going to get 0.05. So a model that would can be used for this situation then, going back here, is F equals 0.05 times D times V squared. Okay, because now I know that constant of variation. So how far does the ship travel on 500 barrels of fuel at 30 knots? Okay, well that 500 barrels of fuel, that's F. It says how far does it travel? I don't know D at 30 knots, so 30 squared. Again, I'm going to solve it very similar to what I did over here. I have to take 500 and I have to divide it by the 0.05 times 30 squared, and I'm going to get D by itself. When I do that, I get about 11.1, and its distance, so it's going to be the same units as this one was, 11.1 miles. Okay, so if you had 500 barrels and you're going at 30 nautical miles per hour, so faster, it's going to use more fuel, but you have more fuel to begin with. You can go a little bit farther, 11.1 miles. Okay, so similar to direct variation, you guys. And you guys have the assignments, but here's what I'd like you to do, and I'll put that on Google Classroom and have you guys turn it in. If you need to look at other videos, Khan Academy, YouTube, feel free to use whatever you need to help you out.